Hello, and welcome to today's lesson in pre-calculus on exponential functions. To this point in time, we've dealt with functions where if we've had an exponent, the exponent has been some sort of a number. It's not been a variable. The difference between those functions, which were polynomials and radicals and things like that, and exponential functions, is now the variable is going to appear in the exponent. And that causes growth patterns that are very different than if the variable is in the base. So we're going to learn what exponential functions are, how to graph them, and in the second video we'll look at functions with base e. Yes, e is a number despite everything you knew to this point in time. And we're going to look at compound interest formulas also as a practical business application. So next slide. Sorry. Next slide, here we go. So what is an exponential function? Well, in a polynomial, we've dealt with polynomials before, right? In a polynomial, the variable is the base and the exponent is a number. In exponential functions, we turn that around. So when we have exponential functions like this, what we see is the exponent contains a variable. This is a fairly basic exponential function. 3 is what we call the base, and x is the exponent. And that's one way to remember what's the deal with exponential functions is x is the exponent. So base b and exponent x is just the generic way to say the way we calculate y in an exponential function is we have a base b and we have an exponent x. And then when b is bigger than 0 and not equal to 1, we get what we call exponential growth. Now, this says where b is greater than 0 and not equal to 1. Now this one here, g of x, b is not greater than 0. You can have b between 0 and 1. And greater than 1. You just can't have it. So you have b when b is bigger than 0. That's always going to be true. You can't have a negative base and be an exponential function. Negative bases do other things. You learn that's how we create alternating functions when you go further in math using a base of -1. But for now, our bases are always positive. And then not equal to 1, because if I had 1 to the x, no matter what I put in for x, I would always get 1. It would always be just 1. So that's not very useful. But b is greater than 0, but when b is greater than 1, we have growth. When b is between 0 and 1, as in the case of g of x here, we have decay. The function will get smaller as time goes on. And in this case, we have a b of 3, the base is 3, so it's growing, and this is also a shift. We can shift our functions. This x plus 4, the 4 is added with the variable. It changes the horizontal position by moving it 4 to the left, just like when we did our function shifting for other functions. This all works the same with exponential functions. So, these are not exponential functions. For this first one here, the reason it's not an exponential function is because the x is not in the exponent. That's a polynomial. It's actually a monomial. This one is not an exponential function because the base is negative. What this would happen is if you said x had to be an integer, every time x went up was even, you'd have a positive value, and a positive 1 every time x was odd, you'd have a negative 1. You use that in things like alternating series, but it's not. But this one is not exponential. This one's not exponential. 1 to the x, we just discussed, that's always going to equal to 1, so that's not a very useful function, though your calculator will allow you to do it. It's not an exponential function. And x to the x is not an exponential function because even though there's an x in the exponent, you need to have a number between 0 and 1 as the base in order to be an exponential function. So, we just said why these are not. We just did this, so I'm going to move on. And, oh, sorry, I don't know why this is doing this to me today, but it is. So when I have 3 to the x, let's consider f of x equals 3 to the x. Okay? I have the base is 3 and the exponent is x. Now, if I'm asked to find, so this is my f of x. If I'm asked to find f of 4, I have a 4 here, and I put a 4 in for my x. F of 4 will be 3 to the 4th. And I want you all to try this in your calculator. In some calculators, you're going to do 3 with the caret to the 4, and in some calculators, you're going to use, in scientific calculators, you might have this y to the x. You all should try this in your calculator and make sure you can get the result of 81. If you can't, drop me an email and let me know what kind of calculator you have, and I'll get you some instructions. But these two sets of instructions here generally cover the two possibilities. So 3 to the 4th, remember, means 3 times 3 times 3 times 3. So every time you add 1 to this exponent x, you multiply by a factor of 3, and that's where the term exponential growth comes from. You're going by a factor, not by something added. Okay, so now for this one, be very careful here. See this 6 times 3 to the x? Well, the 6 times 3 to the x, people always want to multiply this together. You can't do that. You have to look at this as a coefficient of 6 in front of the 3 to the x. Just like you can't multiply 6 times x and do anything but 6x, you cannot multiply 6 times 3 because the exponent only goes with what it touches. It only touches the 3. If you made this 18 to the x, which I'm not even going to write down because then you'll do it, you're now raising the 6 to the x power 2, and that's not what happens. If I need to find g of 4 for this, I do 6 times 3 to the 4th. And by the rules of exponents, you do the 3 to the 4th first, and that's 81. And then you do 6 times 81. That's how you would do this manually. The problem is with our calculators, we lose sight of how this works, and some students decide they're going to do a shortcut, and they're going to do 18 to the 4th. It will not give you the same answer. So here's how you would do it in your calculator. And your calculator knows order of operations. So when you do this, it does not multiply the 6 times 3 first. It looks and says, oh, I have an exponent to do first. Same thing here. It does not do the 6 times 3 first. So don't you do the 6 times 3 first. If you're evaluating these, do the 3 to the 4th first, and then multiply by 6. You cannot multiply that 6 times 3. If you don't learn anything else from this slide or the next 5 slides, you need to learn that because that's a really common mistake. All right. Let's see. Oh, I got a different pen here. Let's see if that works any better. All right. Now, h of x equals 5.22 times 2 to the x. Find h of 4. Same thing. I want you to try this in your calculator. You need to try this in your calculator. Make sure you get the right answer. You do 5.22 times 2 to the 4th first, or 2 to the 1/2 first. I'm not going to continue writing that because that's not coming out very nice. But try it in your calculator. Make sure you're doing the order of operations correctly. If you are not doing the order of operations correctly, then what you should look at is try for the h of 4. What you would do is try the 2 to the 4th first, and you will get 16, and then do 5.22 times 16. If you put it all in one step in your calculator, you should still get the same answer of 83.52. Now, h of 1/2 should be 5.22 times 2 to the 1/2. The other way to think of 2 to the 1/2 is it's the square root of 2. Now, I realize I put multiple parentheses, but sometimes that helps people see that you can't multiply 5.22 times 2 first. And in your calculator, however you do it, whether you do the 2 to the 1/2 first and then times 5.22, make sure you can get this answer. You need to be accurate in these calculations. I'm only asking you to push buttons in a calculator correctly. It's not the hardest math we've done all semester. All right, so the next thing, of course, when we learn a new function is we learn about graphs. I want to graph b to the x. Now notice this time I did restrict b to being bigger than 1, not just 0. This is a growth function. Here is what happens at the point where x is 0. At the point where x is 0, remember anything to the 0 is 1. So you have the point 0, 1 on this graph. If I do b to the first, you'll have the point 1, b. Remember, x goes in the exponent. And if I do b to the negative first, do that up here, I get 1 over b, so I have the point negative 1, 1 over b. And you see that here. Here's your 0, 1. Here's your 1, b. And here's your negative 1, 1 over b. No matter what the base is, if the base is, and this is actually, even if the base isn't bigger than 1, these patterns still hold. It's just 1 over b becomes not a fraction. So if b is bigger than 1, you get this growth. And we've heard a lot about this when we had a pandemic going on. They talked about this R naught of 2.8 and having to get that down. 2.8 was the number they used approximately. And so what they mean to get that down is if that gets lower, it grows slower. And actually what we'll see in the next slide is if we get that R naught less than 1 for a pandemic, we start to get a decay curve, which is the other side. You keep seeing this curve like that. It's kind of a distribution function. But over on the left side of the curve, the base is bigger than 1. On the right here, it's approaching 1. And on the right side of the curve, it becomes less than 1. So you've heard about that. If you followed any news about the pandemic in 2020, then you would have heard about that. This is why they kept saying it's exponential. This R naught represents every infected person. They think on average infects 2.8 people. So some infect 3, some infect 2, some infect 5, some infect 1, depending on your social circles. And that's why staying away from people brings that number down. And once you get that number, so it's below 1, you actually get decay and it goes away. So this is very important to understand exponential functions in the medical field. All right, and here is our exponential function with decay. And it is decay because the function is the base is a fraction. So what if I had a base of 1/2? Why is this decay? If I do 1/2 to the x, well, if x equals 1, I get 1, 1/2. If x equals 2, I get 2. 1/2 times 1/2 is 1/4. That's smaller than 1/2. If the number on the bottom of a fraction is bigger, the value of the whole fraction is smaller. And 3, I get 1/8. Every time I multiply by a half, I get a smaller value, which is what you see happening. So what's happening when the x's are negative here? If I get 1/2 to the negative 1, you have to remember what a negative exponent does to a fraction. If I want to turn that into a positive exponent, I have to swap the numerator and denominator of the fraction. So when x is negative 1, my y is 2. When x is negative 2, my y is 4. When x is negative 3, so as I move to the left, my function goes up. So if I move left to right, which is always the way I analyze graphs, move left to right, I can see I have decay. My y values are getting smaller as my x's get bigger. So when you get a number that's less than 1 as the base of your exponential function, you get decay. And in the pandemic, that was the downside of the curve. They were trying to get it flat so you could not have this peak be too high to overrun hospitals, yet get to the point where it was decaying. Now, that could change if people stop social distancing and start seeing each other. That moves that R naught up again, and it could start to grow again. But the basic idea is you change the base of that exponential function by separating people and making each person who's infected infect less people. And ultimately, you get to the point where it dwindles out. Now, does it ever actually get to 0? Not in a true exponential function, but in a practical one where the numbers are discrete numbers of people, yeah, it will. So, graphs on the previous two slides have similar shape, but the left side and right side are swapped. If we think about this in terms of transposition and moving functions around, transformation of functions, if one graph is f of x, the other is f of negative x. We rotated the graph around the y-axis. B to the negative x is the same as 1 over b to the x. So if I have, sorry, I keep forgetting to pick up my pen here. If I have, and now it won't let me pick up my pen. If I have 1/2, no, this is being silly pen today. Oh, that's why. All right, so Try one more time and then I'm going to give up. There we go. If I have 2 to the negative x, that's the same as 1/2 to the x. If I have 1/2 to the negative x, that's the same as 2 to the x. So if I want to graph 1/2 to the x, I can take a look at the graph of 2 to the negative x and rotate it of 2 to the x. I can take a look at the graph of 2 to the x and rotate it over the y-axis, because when you swap the x's for negative x, you rotate around the y-axis. You reflect over the y-axis, I think is the way we put it in class. So these are the decay and growth are related, definitely. Certainly if one base is b and the other base is 1 over b, you can write one as the other using negative exponents. All right, in your text, we talk about domain. Every time we learn a new function, we learn some things. We learn about domain. You can put any value for x, positive or negative, real number, in for your exponent. So the domain is all real numbers. But what happens when you have a positive number and b is always greater than 0 and it's not equal to 1, although even if it was equal to 1, this would be true. There is no way to take, let's take the number 2, a positive number, 2 to the x. There is no value of x I can put in there. It's never equal to negative 2. You can't do that. It just won't work. And if you remember looking at the graphs, you actually have a horizontal asymptote at y equals 0 that this function does not cross. If it's 1/2 to the x I drew, or if it's 2 to the x, it goes in the other direction. It's a one-sided horizontal asymptote for growth as x goes. So for growth, as x goes to negative infinity, this is for b greater than 1, you get y goes to 0. It never goes below 0. It does not actually cross. Now, if you have a decay situation, as x, that's as x goes to negative infinity for growth. As x goes to positive infinity, y goes to 0. But you never cross it. So you have a left side horizontal asymptote for growth, a right side, but you never cross 0. You cannot get a y value of 0 out of a basic exponential function that's not got anything done to the y. Now, if I put a negative out in front, I can. But your basic exponential function, b to the x, the range is all positive numbers. You can never get 0, and you can never get a negative. And all of the graphs of this basic, unshifted, untransposed b to the x pass through the point 0, 1. So, b greater than 1, we've got that going up. It be between 0 and 1, you have a fraction as your base, and every time you multiply a fraction by itself, you get a smaller result, so the y values go down. So b to the x is a one-to-one function. It has an inverse. Because this function is always either going up or going down, never turns around, it does have an inverse. If you think back to looking at inverse functions from a graph, if I do this, I pass the horizontal line test. Every y will have only one x associated with it. So we will learn about how to find the inverse of these functions using something. The inverse of these functions is something called logarithm. So y equals 0 is the horizontal asymptote. And for growth, you approach that on the left side. For decay, you approach that on the right side. So here is a 3-point way to graph exponential functions. If you simply have an exponential function that's a number raised to the x, you will always have the point 0, 1. You will always have the point negative 1, 1 over the base, which is the number. And you always have the point 1, comma, the number. So here's an example. Now, 0, 1, negative 1, 1/3 for 3 to the x, 1, comma, 3. And that's because the 1/3 is sometimes what confuses students, because we still haven't quite got a hold of our negative exponents. Negative 1 means I do 3 to the negative 1. 3 to the negative 1 is the same as 1/3. So when x is negative 1, y is 1/3. Now, when I have a base that's a fraction, I still have that 0, 1. 1/4 to the 0 is still 1. 1/4 to the first is 1/4. But what happens when I do 1/4 to the negative 1? It gives me the reciprocal of my fraction. In the case of this goes with the whole fraction. 4 over 1. So I get the point negative 1/4. So those are ways to get 3 points. And then if you have a function that's shifted, if I had, say, 3 to the x plus 5, I could now take each of my x coordinates and shift them 5 to the left for my basic function. I would make that a -5, I would make that a -6, I would make that a -4, and I'd have 3 points on my new function, my transposed function. So here is a summary of transformations of functions as applied to exponential functions. You might find this handy as you do some graphing. You can use the 3-point method and do this shifting, or you can pick values for x to plug in. It's convenient to pick a number for x that will give you, like x minus c equals -1, x minus c equals 0, x minus c equals 1, because that will make sure you get that curved part of the graph. You can graph more points than that, but you have to make sure that you kind of pick up on that curved section where it is less linear. And that's what the 3-point method will give you. All right, so let's take a look at how we would apply these transformations. So this is how I would do it. Graph the basic points for each function. In the case of 2 to the x minus 3, the basic function is 2 to the x. So these points here would be for 2 to the x. Now, I look at 2 to the x minus 3, and I say that moves my function 3 to the right. Moving to the right means I add 3 to the x's. So, if I'm adding 3 to the x's, 3, 1, so this 0 becomes a 3, this 1 becomes a 4, this -1 becomes a 2. These are the points on the graph of my function that I've been given. So that's one way to do the transformations. Another way is to just directly plug in the 3, the 4, the 2, but the trick is knowing that those are the 3 numbers you have to do. So what you could do, x minus 3 equals -1. And that gives you x equals 2. Then do x minus, and then just go up from there. Go down, or rather go down from there. X minus 3 equals 0 gives you x equals 3, and then you go up from there. X minus 3 equals 1 gives you x equals 4. If you'd rather just pick 3 values of x and plug directly in, I like doing them by the transformation because we've already learned that and it refreshes those skills. All right, in our next video, we're going to look at the number e. We're going to stop this for now and come back for part 2 later.